In February 1976, Bill Gates was just 20 years old. He sent an open letter to America's computer hobbyists, and it got straight to the point. Most of you steal your software. The software was Altair Basic, a program Gates and Paul Allen had written for one of the first popular personal computers. Hundreds of people were using it. Very few had paid. Gates argued that software took months to build and tens of thousands of dollars to test. If everyone copied it for free, who would pay programmers? Who would fund the next program? Today, that argument can sound almost obvious. But to many hobbyists who received the letter, Gates was the one breaking the rules. They had grown up in a computing culture where code was shared much like scientific knowledge. If you found a bug, you fixed it. If you added a feature, you passed it on. Programs circulated through universities, laboratories, and computer clubs because sharing was how computers improved. Now Gates was drawing a different line. Sharing was no longer cooperation. It was theft. Code was no longer something a community could inspect and change. It was property. Both sides believed they were protecting the future of computing. Gates believed software would never become a real industry without ownership and profit. His critics believed that if every important program disappeared behind a corporate wall, the digital world would be controlled by whoever owned the keys. That argument never went away. It produced GNU, Linux, the open source movement, and much of the infrastructure beneath the modern internet. Today, it is back in a new form, inside the fight over artificial intelligence. But it did not begin with Bill Gates. It began 7 years earlier, at Bell Labs, with an abandoned computer and a programmer who wanted to play a game. In 1969, while the world watched Apollo 11, Ken Thompson was dealing with a much smaller problem. He had written a space travel game, but the computer it ran on was going away. Bell Labs had just withdrawn from Multics, an ambitious operating system project with MIT and General Electric. Thompson had used the Multics machine to develop space travel. When Bell Labs pulled out, he lost the machine, and with it, a practical way to run the game. In a corner of the lab, he found an old PDP-7. It was underpowered even by the standards of the day. To make space travel run on it, Thompson began building the basic tools the machine lacked. Dennis Ritchie soon joined him. File by file, command by command, those tools became the beginnings of a new operating system. Its early name, Unix, was a play on Multics. The spelling eventually became Unix. One of the most influential systems in computing history began, in part, because a young programmer wanted his game back. At first, Unix was rough, but it was built around ideas that were unusually powerful for the time. It could support multiple users and run more than one program at once. It relied on small tools that could be combined, rather than one enormous piece of software that tried to do everything. Then, in 1973, Thompson and Ritchie rewrote most of Unix in C, the language Ritchie had helped create. Most operating systems were still tied closely to the hardware they had been written for. A system written largely in C could be moved to a different kind of computer without being rewritten from scratch. Unix was no longer merely useful. It was portable. Universities and research institutes began asking Bell Labs for copies. Under normal circumstances, AT&T, the company behind Bell Labs, might have turned Unix into an expensive commercial product. But AT&T was no ordinary company. It controlled most of America's telephone system, and the US government had spent years trying to limit its power. Under a 1956 antitrust consent decree, AT&T faced strict limits on entering businesses outside regulated communications. Unix did not fit neatly inside the telephone business, so AT&T licensed it to universities and research institutions for relatively modest fees, often with source code included. There was another condition: little or no technical support. If Unix broke, a university could not simply call Bell Labs and expect someone to repair it. Professors and students had to open the code, work out what had gone wrong, and fix it themselves. It sounded like a bad deal. It turned into an unexpected experiment. Universities used Unix as both a working system and an object of study. They modified it, added tools, and sent their improvements to one another. At the University of California, Berkeley, that work grew into the Berkeley Software Distribution, or BSD, which became a major branch of the Unix family. The people involved did not think they were giving away a commercial asset. Many saw code the way scientists saw a paper or a formula, something to be examined, challenged, and improved by peers. For a while, three things lined up: the law, academic culture, and basic technical need. Source code kept circulating because its owner could not easily build a conventional software business around it. Users needed to repair it, and researchers already believed that knowledge advanced through exchange, but it did not last. In the early computer industry, hardware was the valuable part. Machines were enormous, expensive, and often incompatible with one another. A program written for one computer might be useless on the next. When a customer paid millions of dollars for a mainframe, the manufacturer commonly supplied operating systems, tools, and sometimes source code as part of the package. This was not pure generosity. Software had little value away from the machine it served. IBM began to change that in 1964 with the System/360. Instead of selling a collection of unrelated computers, IBM built a family of compatible machines. A customer could begin with a smaller system, upgrade later, and keep much of the software it already used. That changed the economics. If one program could run across an entire product family, it was no longer just an accessory to one machine. It could be copied and sold to many customers. The first copy might take years to build. The next copy cost almost nothing. In 1969, facing antitrust pressure as the industry changed, IBM announced that much of its software and technical support would be priced separately from its hardware. People usually call that decision unbundling. Once software had its own price, it could support its own companies. And once companies depended on software revenue, they had a reason to stop customers from copying the product freely. Around the same time, computers were beginning to leave corporate and university machine rooms. The Altair 8800 appeared in 1975. By modern standards, it barely resembled a personal computer. Early versions had no screen or keyboard. Users entered instructions through switches and read results from blinking lights. Yet it convinced thousands of electronics enthusiasts that a computer could belong to an individual. Bill Gates and Paul Allen wrote a BASIC interpreter for the Altair. BASIC made it much easier for hobbyists to write their own programs. The software spread quickly, and payment did not. Computer clubs were built around exchange. Members shared circuit designs, instructions, and programs. One person copied a paper tape. Another copied the copy. To the hobbyists, this was how a new world was being built. To Gates, it was a business that could not survive. He said the team had spent months developing Altair BASIC and more than $40,000 in computer time, yet only a small fraction of its users had paid. So, in February 1976, he wrote the letter that opened this story. Most of you steal your software. The letter landed at the border between two eras. Code was knowledge, infinitely reproducible, easy to share, and improved by inspection. But code was also labor, written by people who needed time, equipment, and money. Was a program something a community should be free to study and pass on, or was it a product its creator had the right to control? The business world answered quickly. The United States overhauled its copyright law in 1976. Amendments in 1980 made the status of computer programs explicit. Companies also relied on trade secret law, software licenses, non-disclosure agreements, and employment contracts. Increasingly, buying software did not mean owning it in the ordinary sense. A customer received permission to use a program under a set of conditions. Copying could be forbidden. Modification could be forbidden. And instead of readable source code, customers increasingly received only a compiled binary, instructions a computer could execute, but a human could not easily inspect. Software became an industry that supported millions of jobs and created vast fortunes. But it was still a strange product, almost free to copy, yet tightly controlled by law. In the early 1980s, those rules finally reached Unix. After years of litigation, the US government broke up AT&T. The old restrictions that had limited the company's ability to expand into businesses such as computing fell away. AT&T could now treat Unix as a serious product. License fees rose. Access to source code narrowed. Universities and individual researchers found themselves pushed away from a system they had helped improve. This was not just about money. It changed the culture too. Programmers who once exchanged code as members of a shared technical community increasingly went to work for companies and signed non-disclosure agreements. A developer might have exactly the code a colleague needed and still be legally unable to share it. Some people saw this as the unavoidable price of a mature software industry. Richard Stallman saw a betrayal. Stallman worked at MIT's Artificial Intelligence Laboratory, where the old hacker culture was still alive. People there read one another's programs, changed tools when they needed to, and treated the ability to inspect code as part of ordinary technical life. For Stallman, one machine came to stand for everything that was disappearing: a Xerox laser printer. The printer was fast, but it jammed. Worse, it could not alert users when it jammed. People kept sending jobs, only to walk over later and find a growing queue of stalled print jobs. With the lab's previous printer, programmers had been able to change the software and add an alert. This time, Stallman did not have the source code. He heard that a researcher at another university might have it and asked for a copy. The researcher refused. He had signed a non-disclosure agreement. The printer problem itself was small. What disturbed Stallman was what the refusal represented. A programmer had been required to withhold useful knowledge from another programmer, not because the code was dangerous, but because a contract said it belonged behind a wall. By the early 1980s, the MIT community around him was also breaking apart. Many colleagues had left for commercial firms. The shared system they had built was being replaced by proprietary software. Stallman's answer was not to ask one company for better terms. It was to build a complete alternative. In September 1983, he announced that he would write a complete Unix-compatible software system called GNU. The name was a programmer's joke. GNU's not Unix. The goal was a Unix-compatible system whose users could run it, study it, modify it, and share it. For Stallman, free meant freedom, not price. In 1985, he founded the Free Software Foundation to support the GNU project and promote those freedoms. That created a legal problem. Putting code in the public domain would let anyone use it, but it would also allow a company to take the code, improve it, and release the result as a closed product. Stallman used copyright itself to prevent that outcome. The GNU General Public License, the GPL, allowed people to copy, modify, distribute, and even sell software covered by the license. But distribution came with conditions. If you distributed a modified version, its recipients had to receive the corresponding source code and the same essential freedoms under the GPL. Private changes did not have to be published. The obligation applied only when the software was distributed. Stallman called the idea copyleft. Copyright normally helped an owner reserve rights. Copyleft used copyright to ensure that recipients kept theirs. The license turned a social norm, share improvements with the community, into a durable legal structure. The distinction mattered. A company could go bankrupt. A founder could change his mind. A promise on a website could disappear. But anyone who received GPL software also received rights that later owners could not simply withdraw. For Stallman, access to source code was ultimately about what people should be allowed to do with the software on their own computers. Faster development was welcome, but it was not the foundation of his argument. GNU began producing the pieces of an operating system, a compiler, a text editor, a command shell, libraries, and many other tools. By the end of the 1980s, most of those pieces were in place. One crucial piece was still missing: the kernel. The missing piece was the kernel, the core program that manages a computer's memory, hardware, and running processes. GNU's kernel project, later known as the Herd, pursued an ambitious design, but development moved slowly, and a complete GNU operating system remained out of reach. The story then shifted from MIT to Helsinki. In 1991, Linus Torvalds was a 21-year-old university student with a new 386 computer. He had been experimenting with Minix, a small Unix-like operating system designed mainly for teaching. Minix was useful for learning, but it did not give Torvalds everything he wanted from his computer. So he began building his own system. The project grew from a terminal program into something that could manage files and hardware. Torvalds realized he was building the beginnings of an operating system kernel. In August 1991, he posted an announcement to an online discussion group. He called the project just a hobby and said it won't be big and professional like GNU. He originally considered the name FreeX, combining free, freak, and the Unix-style X. But the administrator who placed the files on a server used a different directory name, Linux. People downloaded it. Then they began sending changes back. One person fixed a bug. Another added support for new hardware. Someone improved the file system. Contributors lived in different countries and had never met, but the internet allowed them to work on the same codebase. Torvalds did not wait for Linux to be finished before releasing it. He published early versions, users found problems, and new versions arrived quickly. The faster the software circulated, the more people could test it. the more people tested it, the faster faults could be found and repaired. Years later, Eric Raymond used two images to describe the contrast. Traditional projects were often built like cathedrals, directed by a small group and revealed when the structure was ready. Linux looked more like a bazaar, noisy, distributed, and always open for business. Raymond summarized the apparent advantage in a famous line, "Given enough eyeballs, all bugs are shallow." It was not a law of nature. Large communities can miss serious problems too, but it captured the appeal of development in public. Linux still needed one more decision. Its earliest license allowed people to read and modify the code, but restricted commercial use. In early 1992, Torvalds moved Linux to version 2 of the GPL. That removed the ban on making money. A company could sell Linux. But if it distributed a modified version covered by the GPL, it also had to pass on the source code and the same GPL rights. That decision finally brought two histories together. GNU had created much of a free operating system, but lacked a working kernel. Linux supplied that kernel, and GNU's tools made Linux useful. The GPL gave the combined system a legal foundation that allowed both volunteer and commercial participation, without letting a distributor simply close the shared core. Most people came to call the result Linux. Stallman and the Free Software Foundation argued that GNU/Linux was more accurate because so much of the surrounding system came from GNU. The naming dispute never fully disappeared, but the operating system worked. After nearly a decade of effort, the free software system finally had the kernel it was missing. Linux did not immediately displace Windows on home computers. Its first great opportunity appeared somewhere most ordinary users never looked: the server room. The web was expanding rapidly in the mid-1990s. Every website needed a server program to receive requests and send pages back to visitors. One widely used server came from the National Center for Supercomputing Applications, or NCSA. But after its main developer left, progress slowed. Website administrators began applying their own fixes. Useful patches existed, but they were scattered across different systems and maintained separately. In 1995, a small group of developers began collecting those fixes, testing them, and building on the last public NCSA release. The result was the Apache HTTP server. Apache's first public release arrived in April 1995. In less than a year, it overtook NCSA to become the most widely used web server. That mattered for more than market share. Free software was often described as an idealistic alternative, admirable, perhaps, but not something to trust with the hardest jobs. Apache showed that open collaboration could support essential web infrastructure. Then a public company fighting for survival did something even more radical. Netscape had once dominated the browser market. Then Microsoft bundled Internet Explorer with Windows and used its control of the desktop to push rapidly into Netscape's territory. In January 1998, Netscape made a radical move. Its browser would become free of charge, and the source code would be released. On March 31st, the first code appeared under the Mozilla project. The logic was simple. Netscape could not match Microsoft's control of the operating system or its financial resources, but it might recruit developers across the internet to find bugs, build features, and improve the browser faster than any one corporate team could on its own. Opening the code did not save Netscape as an independent company, but it changed what companies thought open development could do. If a publicly traded company could release the source code for a core product as a competitive strategy, collaborative development was no longer just for universities and hobbyists. It still had a branding problem. Stallman's term was free software. Among supporters, the word free carried a moral claim about liberty. In a corporate boardroom, it often sounded like a claim about price, and therefore the absence of a business model. The label itself created another problem. Stallman spoke about rights, duties, and the social harm of proprietary software. Those arguments inspired a movement. They also made many executives suspect that free software advocates regarded business itself as the enemy. After Netscape's announcement, a group of advocates saw a rare opening to reach the mainstream. On February 3, 1998, at a meeting in Palo Alto, Christine Peterson proposed a new label, Open Source. Later that month, Eric Raymond and Bruce Perens founded the Open Source Initiative. Torvalds and other prominent developers supported the term. The same way of building software now had a pitch designed for corporate America. Free software asked which freedoms a user should never lose. Open source emphasized the practical benefits of visible code. quality, speed, security, and cost. One was primarily a moral and political argument. The other was easier to present as an engineering and business method. Stallman rejected the rebranding. If openness was defended only because it produced better results, he argued, a company could close the code again whenever secrecy seemed more profitable. Efficiency could be a reason to choose openness. It could not guarantee freedom. That divide is still with us. The two camps often use the same programs and licenses, but they do not always tell the same story about why those programs matter. While they argued, Linux, Apache, and other open projects continue to spread through corporate servers and data centers. By 1998, leaked Microsoft strategy papers known as the Halloween documents treated open-source software as a serious competitive threat. Microsoft knew how to fight another company. A company had executives, offices, revenue, and investors. It could be undercut, outmarketed, acquired, or driven out of business. An open-source project was harder to kill. A foundation might disappear. A sponsor might withdraw. Maintainers might walk away. But if the code and its license allowed copying and modification, other people could preserve it, create a new version, and continue. Open source was proving unusually resilient, but it still had one old problem. Who pays the people doing the work? Red Hat offered one of the clearest answers. The company did not try to take Linux private and sell proprietary code. It gathered Linux and GNU components from across the internet, tested them together, packaged them into a usable system, supplied updates, and offered professional support. Red Hat co-founder Bob Young once used ketchup to explain the model. Anyone can get tomatoes and make ketchup at home. People still buy a bottle because it is convenient, predictable, and tastes the same the next time they open one. Red Hat was not selling code nobody else could get. It was selling confidence. An enthusiast could download Linux and solve problems on a mailing list. A bank or telecom company wanted tested releases, security updates, long-term maintenance, and a phone number to call when a critical system failed. The code could remain open while reliability, integration, and responsibility became paid services. Red Hat went public in 1999. In 2000, IBM announced a $1 billion commitment to Linux across products, services, and development. By then, something had clearly changed. A movement that began with one programmer refusing to accept proprietary control was now infrastructure for startups, a strategic tool for established technology companies, and an investment story on Wall Street. Open source did not get rid of commerce. It just changed where people could make money. Rather than making money by keeping code closed, companies could sell expertise, maintenance, certification, hosting, hardware, or a reliable distribution of software anyone was legally allowed to inspect. This worked because the participants did not need to share the same motives. A volunteer could improve a program for personal reasons, a university could use it for research, a hardware company could make its machines more useful, a services firm could make money supporting it. Competitors could collaborate on a shared foundation and still fight over everything built above it. It did not end ownership. It drew a new line between what stayed common and what companies tried to control. If this story had ended around the year 2000, it would have a neat ending. A scattered community of programmers challenged the largest software companies. Sharing turned out to be both idealistic and practical. The code was open, the movement had won, and everyone benefited. But that was not the end. Linux never displaced Windows for most personal computers. Ordinary users continued to see Windows and Mac OS on their screens. Behind those screens, Linux was winning a much larger but less visible battle. Web servers, databases, programming languages, network equipment, and eventually cloud platforms came to depend heavily on open-source software. People could go through life without installing Linux directly while still using it every day. Whenever they opened a website, sent a message, streamed a video, or used an online service, open source was no longer just a rival product. It had become essential infrastructure for the entire industry. The way programmers collaborated also changed again. For years, the Linux kernel project had managed contributions through patches, archives, and mailing lists. In 2002, it began using BitKeeper, a powerful distributed version control system owned by a commercial company. The Linux community received access without paying, but the tool itself was proprietary. In 2005, that arrangement collapsed. The relationship between the kernel community and BitKeeper's maker broke down, and free-of-charge access was withdrawn. The episode brought back an old lesson. If a critical tool remains under someone else's control, permission granted today can be removed tomorrow. Torvalds responded by creating another tool. He called it Git. Version control software records changes to code. Git was designed so that every developer could hold a complete copy of a project's repository and history, create branches, experiment independently, and exchange changes without relying on one central copy. Unix developers had once mailed tapes between universities. With Git, people across the world could work on the same enormous project while preserving a precise record of what changed, who changed it, and when. In 2008, GitHub made coding more social. Developers gained profiles, projects gained discussion and review tools, and contributors got a simple way to submit changes to the original project. Code became a public record of a programmer's work. A young developer no longer needed to join a famous laboratory or be hired by a prestigious company before demonstrating what they could do. A useful contribution to a public project could be read by leading engineers anywhere in the world. Open source had started as a set of permissions. It was turning into a global way of building software and a global job market that made Microsoft's turnaround so striking. In the early 2000s, Microsoft executives described Linux and the GPL as threats to the company's business model. But as the industry changed, Microsoft changed with it. Its cloud business depended on serving customers who used Linux and open source tools. Microsoft increasingly needed to serve developers on whatever platforms they chose. In 2016, Microsoft joined the Linux Foundation as a platinum member. It had already begun releasing the source code for major development tools and bringing Linux environments into Windows. In 2018, it agreed to acquire GitHub for $7.5 billion. For many longtime developers, the announcement seemed almost surreal. The company once seen as open source's most powerful enemy was buying the platform that hosted much of the open source world. It looked like a huge victory. Microsoft was basically admitting that open collaboration had become too important to ignore, but it also brought back an old worry. The code on GitHub could remain open, but the platform where developers stored projects, discussed changes, displayed their work, and found collaborators now belonged to one of the world's largest corporations. Microsoft promised that GitHub would remain open and that developers could keep using the languages, operating systems, and cloud services they chose. But a bigger question was still there. If the code is open but the platform around it is privately controlled, where does the real power sit? 1 year later, IBM completed its acquisition of Red Hat for roughly $34 billion. A business built on software that anyone could copy had become one of the most valuable assets in enterprise technology. What began as a hobbyist alternative had become central to the future of cloud computing. Stallman and Torvalds appeared to have won. The source code was out. The major companies had accepted it. The internet ran on it. But accepting open code did not require a company to abandon the desire for control. It could simply build the walls somewhere else. In the old software business, control centered on the source code. To use the program, customers bought a license. To understand or modify it, they needed the owner's permission. In the internet and cloud era, a company could release large amounts of code and still control the assets that were hardest to reproduce. Servers, data, customer relationships, computing power, app stores, and distribution. Android makes the distinction visible. Much of the operating system is available through the Android open source project. Manufacturers can inspect it, adapt it, and build devices from it. But access to the most valuable commercial ecosystem, Google Play, key Google services, distribution, and user relationships, does not come from source code alone. Das Tolles mein Sohn. A small team might build and maintain an important open source database. A much larger cloud provider could take that code, run it in global data centers, turn it into a convenient service, and earn far more than the people who created the underlying software. The license had done what it promised. The code remained available, yet the economic power had moved to infrastructure and scale. Open source companies began asking cloud giants a question that sounded strangely familiar. In 1976, Bill Gates had asked, if everyone copies the software, who pays the programmer? Decades later, maintainers asked, if a cloud company can take our code, sell it to millions of customers, and keep most of the revenue, who pays the people who build and sustain the project? It was not exactly the same fight. The walls around source code had fallen, but control had shifted to the machines that ran it, the data it produced, and the routes through which it reached users. Artificial intelligence brings all of those pieces together: code, data, computing power, servers, and access to users. And this time, the thing people are fighting over is not just a program. It is a tool that increasingly shapes how people think and work. Large models write, code, search, translate, and analyze. They are moving into education, medicine, finance, and public institutions. As they spread, this old argument is coming back with much higher stakes. Should the most powerful models remain inside the data centers of a few companies? Or should people be able to download, inspect, modify, and run them on infrastructure they control? The comparison with open-source software helps, but only up to a point. A model behaves the way it does because of its architecture, training data, enormous amounts of computing, and a long series of decisions that may never be disclosed. Releasing model weights can create meaningful access without revealing how the model was actually made. That is why everyone is arguing over what open actually means again. When a company calls a model open, what exactly is open? The code? The weights? The license? The training data? The right to modify it? The ability to use it commercially? And what remains closed? Half a century ago, programmers argued over the right to inspect a program and understand what their own computer was doing. Today, that same argument surrounds systems that may shape how people write, learn, search, program, and interpret the world. When all of that runs through models controlled by a small number of companies, their influence goes far beyond one software product. They gain power over the systems people use to ask questions and get answers. The technology has changed, but the dispute over who should control it has not. This is where the software part of the story ends. The next part begins with the models themselves. Why some are released, why others remain closed, what open actually means in AI, and why data, chips, and computing power may matter even more than access to the code. We began with a printer whose users could not inspect the software. Now we are talking about data centers that nobody outside the company can enter. The old fight has moved, but it has not gone away.